see if like y becomes like a y1 plus b y2. So like, yeah, you just test for like linearity.
What about the zero thing?
That's what I was talking about. That's it.
Never knew D?
That's for linearity, and that's it.
Okay. So I said linear.
That's like all you have to do, like work, right? So we got a new problem set after this, and then we're gonna come to office hours to finish it. And then probably I'm actually starving as well. Is that the one you want had to build a chemical plant, and like the budget got cut, so he had to like cut a bunch of corners. Like pretty much all the higher ups were like, you know, forced him to like do shit. He was like, "Whoa, this is like bad," and we were like, "No, you're our bitch to do this." Like, it all ends up like cutting so many corners, and like some guy ends up dying. And, like he gets to like go into like
Okay, let's continue with the lecture.
get no backup to you. Love the element. Stand up for yourself. He even came over from he worked competing with chemical plants and like designed their plant with the higher in the first place. So like, dude, better secrets. They ended up killing him.
Dude, this is BS. These are the two terms.
Okay, let's continue with chapter 11,
These are the terms.
section 11.3 is what we're supposed to cover today.
YT is you just did it right now.
So we're supposed to do is S domain circuit analysis. So this is actually the third time you're doing this. First we actually talk about phasor circuits, how you, if you're faced with an inductor or capacitor, if you use phasor circuits, those circuits become a lot simpler. And then we work with Fourier series, and then we work with Fourier transform. Now we work with Laplace transform. Actually, they're much of the same thing. Okay? So if you have some VI relationship for an inductor that looks something like this, if you Laplace transform this equation, so you just get something like S L I hat S. Okay, what happens is that ddt just becomes S. Okay, S in the Laplace transform domain. And the same kind of repetition goes that you have learned in phasors, Fourier series, Fourier transform, and now Laplace transform. Okay. And so if you have a capacitor, you have the VI relationship been looking like this, then this would just be SC, V hat S. And then the same kind of things go as we had before. Okay? So I think this is a lot of repetition here. I will not go into great details, but the fact that impedances can have three forms. That for an inductor it becomes SL, for a capacitor it becomes one over SC, for a resistor nothing changes. Okay, this is a capacitor, this is a resistor. Okay, so let's do example 11.22. And that you have a circuit that looks something like this. F of t with a resistor R and an inductor L. Then in the Laplace transform domain, this circuit just becomes very much of the same thing, but the voltage source becomes F hat of S, and then resistor remains the same, but the inductor becomes SL. And you just solve this circuit. Okay? So, in this example, I think it's given that L R is equal to 1 and L is equal to 1. Okay. R equals 1, L equals 100. Okay, so you can figure out that y hat of S is the voltage across here. Okay, y hat of S is just equal to S over S plus 1. Remember that all these are 1 now. Okay, L is equal to 1. So this is just a voltage divider formula times F hat of S. Okay, and then the transfer function then, which is equal to output over input, okay, is just equal to S over S plus 1. And that's the transfer function. And then you're given that the input f of t is equal to e to the minus t ut. Okay, this is the input. And then you find the Laplace transform. Okay, there's a 2 here, sorry. There's a 2 here. Okay, there's a 2 there. I think there's a 2 over there. Yes. There's a plus 2, sorry. There's a plus 2 over here. So you can find f hat of S. F hat of S is just equal to 1 over S minus 2. Okay? And then you can find y hat of S. Y hat of S is equal to the transfer function times this thing, which is 1 over S minus 2. Okay, so the next thing that you need to do is do what? Partial fraction, right? You do partial fraction, and if you do partial fraction of this, you get 1/3 S plus 1 plus 2/3 S minus 2. Okay? Do you need me to go into the partial fraction in greater detail? Or I presume that you know how to do that. Yes?
Can you please?
Okay, good. So let's first write this out as K1 over S plus 1 plus K2 over S minus 2. Assuming that it can be done that way. What are the checks that you have to make sure that you can write things in this form? There are 2 checks that you have to make. One is that the left-hand side must have something before you can write it in this form. Left-hand side must rational polynomial, that's one of them, yes, but right, the denominator has to be of a higher order polynomial compared to the numerator. Okay, in other words, when S goes to infinity, the left-hand side vanishes. The right-hand side also vanishes when S goes to infinity. So these 2 equations are balanced and possible only if when S goes to infinity, the left-hand side vanishes. Okay, what are the other checks that you have to make? Does anybody remember the second check we have to make to make sure that we can write it in that form? Yes?
There can't be any repeated roots involved.
Right, no repeated roots. Okay, if the poles are repeated, you have to add an additional term. If these are simple poles, then you can write it in this form. Then simple poles can be balanced by simple poles. Okay? So you have this equation. The first thing you can do is to multiply by S plus 1 to get one equation. If you multiply by S plus 1, then on the left-hand side you just have S plus 1 cancelling with S plus 1, you have S over S minus 2 on the left-hand side. On the right-hand side you will have K1. This S plus 1 will cancel with that S plus 1, then you have K2. S plus 1 over S minus 2. And then in order to find K1, what must you set S to? You set S to -1. Okay? This vanishes. This becomes -1 over -3. And this becomes K1. And this one is equal to 0 when you set S equal to -1. So K1 is one third. Okay? And for the same token, in order to find K2, you multiply by S minus 2 and go through the same argument as before. And if you do that, then you will have this term canceling with each other. You have that on the left-hand side. And then you have K1 S minus 2 or S plus 1. And then you have K2. If you multiply by S minus 2, you get that. And now you set S equal to 2. You set S equal to 2, then this term vanishes. K2 is 2 over 3. S is equal to 2, so it's 2 over 3. Yeah, that's right. K2 equals 2 over 3. So this is my K1, this is my K2. Okay? Then the next thing you need to do is to do a table lookup. Table lookup for the Fourier or the Laplace inverse transform of these two functions. A function that looks like a pole, a function with a pole in a different location. So y of t can be done by the table lookup. And so this has a pole on the left half plane. If you look at this pole, that pole is at s equals to -1. Okay? And then the other one has a pole on the right half plane. S is equal to +2. So when the pole is on the left half plane, that could only be contributed by what kind of function, if you can recollect from your lookup table. So it must be e to the minus t ut. Okay, this is exponentially decaying. It's a very stable function, so it must be corresponding to a pole on the left half plane. And then this one is an unstable pole because it's on the right half plane. So this must Fourier inverse or Laplace inverse transform to something like 2/3 e to the plus 2t ut. So those are the two solutions that you have. Okay. So that is pretty much it. And it is some work in Laplace transform, and then on how to convert a circuit into the Laplace domain and then work on that. Okay, let's do another example. This example being a voltage source driving a resistor plus an inductor plus a capacitor. And if I have this circuit, if I take it to the Laplace transform domain, it will look something like this. This voltage source will be replaced by that, and then resistor remains the same. This replaced by SL, and then this being replaced by 1 over SC. Okay? And in this example, everything is 1. Okay, everything is set to 1. So R is 1, L is 1, and C equals 1. Okay? You're supposed to find the function y hat of s, which is actually the current y of t. Okay? You're supposed to find this ratio, h hat of s, which is called a transfer function, which is y hat of s divided by f hat of s. So y hat of s is the current that goes through the circuit. So you can see that y hat of s must be equal to the voltage divided by the impedance of the circuit. The impedance of the circuit is 1 plus s. L is 1, remember, plus 1 over s. Okay, Those must be the relationship between ys and f of s. Okay? So you work this out, then you have h hat of s being equal to this divided by that, which is 1 over 1 plus s plus 1 over s. And then of course you multiply this over s, so you get s over s plus s squared plus 1. Okay, you multiply out by s, you get that. So you have a, let me see, do I get the same? Okay, there's a 2 somewhere. Let me see where's the 2. This is a 2, sorry. This is a 2. So this is a 2, so r is equal to 2. So this must be a 2. And this will become 2s. Okay? So, now if we factorize the numerator and denominator whenever we could, then we have h hat of s being equal to s over s plus 1 squared. Okay? This is just s plus 1 squared. This thing over here. You can complete the square and notice that this is just s plus 1 squared. Then the next thing we need to do is the partial fraction. Partial fraction extension of this thing. Now we have repeated poles. We have repeated poles, which means that I can write it as k plus k1 over s plus 1 squared plus k2 over s plus 1. Okay? So in order to find k1 and k2, I do the same as I did before. I multiply the whole equation by s plus 1 squared. If I do that, then on the left hand side I have s, on the right hand side I have k1, and then on the second term I have k2 s plus 1. Okay, that is what I have. And if I set s to be minus 1, okay, if I set s to be minus 1, I get this term to be 0, I get minus 1 is equal to k1. So k1 is minus 1. Okay. In order to find k2, actually I can set s to anything. S is equal to minus 1 plus k2 s plus 1. Okay. You can set s to anything. You can set s to 0. I get minus 1 is equal to k2. Or k2 is equal to 1. So I get k1 to be minus 1, k2 to be 1. Okay, so in order to find k2, you can set the equation with s to anything that you wish. And you always pick the simplest value, which is to set s to 0 to make the equation the simplest. So I have this partial fraction expansion that this being equal to minus 1 over s plus 1 squared plus 1 over s plus 1. Okay. So now I need to find the Laplace inverse transform of these two functions. Okay, Laplace inverse transform of these two functions. And what is the Laplace inverse transform of 1 over s? What does the inverse Laplace transform to?
U of t?
Yes?
Direct delta?
U of t, right? It's very good. Okay. And what about 1 over s squared? What does it Laplace inverse transform to?
T u t?
T u t, very good. Okay, T u t. And hence you can find that 1 over s plus 1 squared. What would this inverse Laplace transform to?
T u of t e to the minus e to the 1.
Very good. Okay, e to the minus t. Okay, this is like the frequency modulation formula applied backward. This is like a frequency shift. So in the other domain, it's being modulated by e to the minus t. Okay. And then you can also figure out from this 1 over s plus 1 must be Laplace inverse transform to that. So finally, you will have ht, h hat of s goes to ht, and you can just put these two together. Okay, which is there's a minus 1 here, which is 1 minus t e to the minus t ut. Okay? Is this clear to everybody? I guess it must be. It must be clear to everybody. And then we have another circuit example. Example 11.24. Let's see if it's worthwhile going to 11.24. It's an op-amp example. And then 11.25 is the control voltage source. Yes, Alex?
Can we find h of t not using like Laplace transformations? Like, can't we use it using other methods gone through the course, or do we have to use Laplace to calculate these for these circuits?
Oh, you could find it using Fourier transform if you want to. You can find it using phasors. I guess phasors not yet. Okay, Fourier transform if you want to, and then Fourier inverse transform as well. You will get the same answer.
So what's the benefit of Laplace is what I'm asking.
What is good about Laplace? Wow. Let's see what is good about Laplace. Well, you can have exponentially growing functions. It allows for exponentially growing functions. If I make this f of s exponentially growing, you can still find a solution to this problem, whereas Fourier transform does not allow that.
So it's basically for functions that we don't have an easy time finding the Fourier transformations of, we can find the Laplace transformation and then solve the circuit that way.
Right. You realize that Laplace transform is nothing but a kind of generalized Fourier transform. Say if f of t does not have a Fourier transform, perhaps for the reason that it becomes like that when t tends to infinity, this is not absolutely integrable and hence not Fourier transformable. Then you can always define a function, okay, maybe called f hat of t, maybe not f hat g of t, okay, and this thing would tend to minus sigma minus at when t tends to infinity, and if you pick sigma larger than a, this has a Fourier transform now, and this has a Fourier transform, and you can use Fourier transform technique to this. And Laplace transform is nothing but this. The trick that you add an exponential decaying function to crowd the rise of the exponential growth so that you have a Fourier transform, and then you can go back and forth. Okay? So Laplace and Fourier transform are actually close cousins of each other. Okay, they're very similar, except that one person calls it S, the other person calls it J omega. Okay?
How far apart do they live?
They must be all French, right?
Yeah.
Joseph Fourier and Laplace, they were all Frenchmen. So they must be fighting.
Or not fighting.
Or not fighting.
Because they're French.
But the three musketeers, right? They're all French. They fought.
So, is there any function that you cannot solve? I mean, you can only solve by the Laplace transform.
Well, this is an example. This thing, this function is no Fourier transform because it's not absolutely integrable.
Oh, okay.
But you can do Laplace transform. Laplace transform is similar to doing this trick. Okay, you define a new function so that it becomes exponentially decaying, and then it has a transform. Okay, so it's just nothing but the trick. Okay, so I have two examples left. One is on op-amps, the other is on voltage control source. Which one do you want to do? Op-amps or? Let's do the voltage control source thing. Okay. I think that's it. Well, we can even do both if we have enough time. Okay, let's do the example 11.25 first. Example 11-25. Okay, you are given this circuit with a voltage source here, a resistor, a capacitor, and then a resistor, and then a resistor here, and then a control voltage source. This is A, B, X hat of S, okay? And then let me see, before you get to this one, you actually have a and this one is plus or minus B, X, S, okay? This is F of hat S, this is a voltage source, this is a control voltage source, and this is an R, this is a C, this is an R, and this one is also an R. Okay, R is equal to 1 here, R equals to 1 here, C is given to be 1 as well, everything is 1. Okay, C equals to 1, R equals to 1. Okay? So you're asked to solve this problem using Laplace transform. Very similar to what you have done with phasors and Fourier transform, except that j omega becomes S. So the first equation you write down is that we had S, which is the voltage here, okay, divided by the this thing is going to be equal to this voltage minus this voltage. This voltage here is going to be, by definition, A, B hat S. Okay? This voltage minus this voltage, which is this equation over here, then divided by the total impedance that I have over here, which is R plus 1 over j omega c, so it's 1 plus 1 over S. Okay, that is the total impedance I have in this section over here. And that must be equal to the current that is flowing this line. Okay, that current is also given by this one divided by 1. Okay, this voltage source divided by 1 gives me the current on the resistor. That must be equal to this voltage source minus this voltage divided by the impedance of this section, which is that over here. So I have an equation 1, okay, and I can solve for my B X hat of S in terms of f of S. I get something like S over S into 1 plus A plus 1 times f hat of S. Okay, it's just a simple algebra, and if you go through the algebra, you will get this to be the first relationship between this voltage and that voltage over there. Okay, the second equation that you should write is on this side over here. On this side over here, you have to write the fact that I have another thing called y of s. Okay, y of s is that thing over there, and that is the voltage across this resistor 1. Okay. Y hat of s must be equal to A. Let me see if it calls it the resistor. Okay, the voltage must be just equal to A V hat S divided by 2. Okay, because if I use the voltage divider formula, this is equal to 1 over 2. This voltage across here compared to the total voltage is just 1/2. So this voltage must be half of the voltage that has been seen here. Okay, so this is equation number 2. And then I have to find my H hat of S, which is defined to be Y hat of S divided by the input F hat of S. Okay? But I know Vx of hat of S is given to be this. I can substitute that in there, okay, and obtain the relationship between this and that by doing some algebraic manipulation. And so what you get is something like A over 2 into 1 plus A, and then divided by some of this thing that you have over here, okay? And you get S over S plus 1 over 1 plus A. Okay, that is my transfer function that I get. You want me to go into some detail in deriving this, or you are acceptable and it's okay that you accept that as the answer? I can also derive it in greater detail by first substituting this into the right hand side. I get Y hat of S being equal to half A, and then put that in there, which is S, and then S into 1 plus A plus 1. Okay, I just substitute that. I get this equation, then I'll obtain this divided by that being equal to A over 2 times S times 1 plus A. Did I get it right? A over 2, 1 plus A plus I get the equation that looks slightly different from what I have. And is this the same as what I have above? Oh yeah, it's the same as what I have above. Okay? I can rewrite this. I can take the 1 over A out and write this as A into 2 into 1 plus A. Taking the 1 over A out, I get S into S plus 1 over 1 plus A, which is what I have above. Okay? So I have my transfer function. The next thing is actually to decide if this system is bibostable. And you actually do not have to find the Fourier inverse transform in order to decide if it is bibostable. You just have to look at where the pole is. The pole location is given by pole is given by S equal to minus 1 over 1 plus A. Okay, that is the location of the pole. Okay, so if this thing is negative, then it is bibostable. Okay, if it's negative, it's bibostable. And that means that A, or I would have something like so if A is larger than -1, if A is larger than -1, okay, if A is larger than -1, you will make the denominator negative. You will make the denominator negative. And then this would not be stable, right? The pole is at this location, so I need this to be negative. And then if A is larger than -1, okay, then this will remain negative. Okay, if A is larger than -1, it means that 1 plus A is larger than 0. Okay, 1 plus A is larger than 0, which means that this remains positive. 1 plus A is positive. Then 1 over 1 plus A is negative. Okay, this implies the pole is on the right half or left half plane. This means that it has to be bipole-stable. Okay, if A is less than or equal to -1, which is the opposite of this, it implies that it's bipole unstable. Okay? I think this is the example I have to show. And let's see if you can not do the op-amp example. You can work that out yourself. Okay, and let's do some examples from section 11.4. Let's move over to section 11.4. And section 11.4 is about transfer function. Again, nothing to do with circuit anymore. Okay, you're given that the transfer function, at least all the transfer functions that we have done for this course, is a ratio of two polynomials. One in the numerator and one in the denominator. And that the one in the numerator can be expanded in terms of a